This is problem 14-18. The gear system shown in the figure below is used to raise the load L. If the system is initially at rest and a constant torque motor attached to the smaller gear A gives it a constant angular acceleration of alpha A equal to 2.5 radians per second squared, determine A, the amount of time required to raise the load L to a distance of 5 meters, B, the number of revolutions in sub B that the larger gear turns while lifting the load L a distance of 5 meters, and then the velocity of load L when it has risen 5 meters. Okay, so I just want to remind you again that these problems are all giving us motion values only. We don't know how strong the motor is. We don't know how heavy the block is. Those are coming soon. Those are coming in the next section, next chapter. Not next section, but the next chapter, chapter 15. And so we are being told how this thing is moving. So we are only calculating relationships between the motion of one thing, the physical characteristics of another, and how that other thing is moving because of these physical interactions based on geometry only. Okay, so let's take a look at this problem's math. So we are given that there's some load L and that the angular acceleration of the gear A is, okay, some of the given information we have is first that the system is initially at rest. And so we can say that the initial velocity of L is equal to 0, the angular velocity of the gear. So let's say the gear is equal to 0, okay? And then they tell us that the smaller gear A gives a constant angular acceleration of alpha A equal to 2.5 radians per second squared. Okay, so I'm not going to put a lot of detail into this, but we have the smaller gear A and the bigger gear, we'll call it B, and then we have the load L, just so we can keep track of things. And then that means that I want to put that the angular velocity at the beginning is A, and this is an initial, right? Which also means that the angular initial velocity of B is equal to 0. All right, but they only tell us the acceleration of gear A. And they want us first to calculate the amount of time required to raise load L a distance of 5 meters. So somehow this load will end up going 5 meters due to the acceleration of A, the angular acceleration to be specific. Okay, so what other things do we know? Well, in the diagram, they showed us that, I'm going to move the A out of the way here a little bit, that the radius of this gear is 0.17 meters. Okay, and then the radius of B is 0.3 meters. Okay. We can use the ratio of the size of the gears to find out what the linear velocity of the cable being pulled into the larger gear will be by using a relationship between angular and linear motion. Okay, but first, really the only useful information we have as far as motion is concerned is the acceleration. Okay, and we know we start at 0. So as usual, let's go ahead and integrate the acceleration, in this case, the angular acceleration, and get an angular velocity and an angular position if we need it. All right, so let's go ahead and integrate alpha of A to omega A, right? And then that equals 2.5t, and that'll be plus 0 because we were already told that the initial velocity is 0. Now, we have to think about these gears. When gear teeth interact with each other, so I'll try to draw like some sort of teeth. I'm not going to go into the same detail as the picture. So there are some teeth on these gears, right? And they are linked together. And so the gear will maybe turn this direction, but then that'll force A to turn the other direction. Right? So A and B will turn together. This may not be the direction that they are turning in the problem, but that means that the linear velocity between the teeth as they move are going to be equal to each other. All right? How do we find the linear velocity of a rotating object? It's the radius times the angular velocity. So if we know that the radius of A and the angular velocity of A is equal to the velocity of the teeth, and the teeth are connected to each other, then we also know that the radius of B times the angular velocity of B is also equal. All right, we know the radii of the two gears, and we can find the angular velocities, hopefully, in some way. All right, we do know the function of the angular velocity of A. All right, but we don't know the angular velocity of B because we weren't given an acceleration for B. All right, so then let's go ahead and see if we plug these values in and have them equal to each other, what we can get. So we know that the radius of A is 0.17 and that the angular velocity of A is 2.5, I mean, as a function of time at least. Okay, and then that is equal to the radius of B, 0.3, which is equal to the angular velocity of B, which we don't know. All right, so what we can do is we can solve for omega B, and it will have a t in the function. So basically, we just found omega B, the angular velocity of B, as a function of time. So if we solve for that, it's 1.42 t radians per second. All right. So now if we want to find how far B rotates from the beginning of this system's movement until L is 5 meters up, we need the angular position, and then we can do a transformation to find the linear distance. Okay, so first let's do the integration. So the angular distance, the angular position of B is going to equal the integral, all right, which ends up being 0.708 t squared. Remember, it's just 1.42 divided by 2. Okay, and then we can say that the initial position is going to be 0. All right, so now we have to know when we get to a particular position or something like that. So what do we know? We know where, over here, we want to find our new position. But this 5 meters is a linear change in distance. We need an angular change in distance. So the relationship for finding a linear change in distance, the book likes to use S, is going to be the radius of B times the angular position of B. Now, we need to then know what the angular position will be in order to know at what time we are at the 5 meters. Well, the 5-meter change is going to be related to the gear beam moving, and the gear beam moving angularly is going to be 0.3 times whatever its angular position happens to be, just like I had said before. Okay, so that means that what we can do is we can put 5 in for S. We know that we have 0.3 for the R. And what is theta? Theta is this function down here. So then we can just put 0.708 t squared, and we can get the time. You also could have solved for theta b and plugged the s and the r into the theta down here. Same thing. Maybe some of you were thinking that's where I was going to go with that. It's the same thing, just a slightly different order. Okay, so then t is equal to 4.85 seconds. All right, that's when the load is raised 5 meters. So that's the answer to part A. Then it wants to know the number of revolutions that the larger gear turns while lifting the load L a distance of 5 meters. Okay, well, we just plug the T into the theta equation, right? That's pretty straightforward. So theta B is equal to 0.708 times 4.85 squared, right? That ends up being 16.67 radians, right? 16.67 radians for perspective is roughly equal to 2.65 revolutions. All right, so that is the answer to part B. Part C, the velocity of load L when it has risen 5 meters. All right, well, we have an angular velocity equation for B, and that is omega B equal to 1.42 times T. And we know when this is happening, okay? So we can find the angular velocity, but then finding the angular velocity is not really the question. It wants the load velocity, the linear velocity going straight up. So the speed at which the outside of this gear rotates is going to can be translated to the linear velocity of L. So if we were to calculate omega b, well, first let me say that the velocity of the load, which is also the velocity of the outside of gear B, the circumference of gear B, is equal to the radius times omega b, the radius of B times omega b. Okay, so then that ends up being 0.3 times omega b. What is omega b? Omega b is 1.42 times t. So 1.42 times t, but t is the time of 4.85 seconds. So now we have, just to recap, we have the radius, we have the, and then we have the angular velocity, which is 1.42 times the time that we care about. That ends up equaling 2.06 meters per second. This is linearly. This is how fast the velocity of L is when it's at this location, continuing to go up.